So I just remind you, before the break we defined non-iterated version of Shtukas. Let me just give one example comparing the iterated version and non-iterated version. Again, we use this Drinfeld example, two legs. So there's a map from iterated version to non-iterated version. If we choose an ordering, but it's not an isomorphism. So So let's compare the first moduli space. Well, in both cases, we need to choose 2 points as legs. The first one has a vector bundle that's inside both E0 and its Frobenius pullback, such that the first map has some drop at x1. The second map has a drop at x2. So this is the iterated version. And the non-iterated version, we don't have the middle guy. We just have a rational map. And this rational map has some conditions. So we only define it as the image of whatever can be obtained from this data by forgetting E1. Okay? So at least we know this has, at worst, a simple pole. So simple 0 at x2 and a simple pole at x1. It cannot be, poles 0 orders cannot be too large if it comes from such a diagram. But there's even more simple, for example, pole, and you look at the leading term, there's more constraints. Now let's look at where this fiber fails to be a point. Okay, so if x1 is not equal to x2, then there's a unique way to put an E1 here. If it comes from such a thing, then this middle guy can be recovered. Because modifying your bundle at 2 different points can be done separately and in any order. When x1 is equal to x2, there are 2 cases. Either the map alpha is not an isomorphism, or it is an isomorphism. In the first case, again, there's a unique E1. In fact, in both cases, you can just take E1 to be E0 intersect tau E0. Intersect in the sense that they have the same generic fiber. Or alpha identifies the generic fibers of these 2 bundles. Then we can intersect them. In the last case, there are many choices. Right? So there's a Pn-1 worth of choices for E1. You can decrease your bundle at x1 in any direction, along any line in the fiber. So the conclusion is that over such a case, such a point, the fiber of this map is isomorphic to Pn-1. Otherwise, it's an isomorphism. Okay. But the dimension still is it doesn't affect dimension. This has absolute dimension 2n. This also has absolute dimension 2n. Okay, so just one example. Now, I will talk about two very important constructions on the moduli space of Shtukas. One is Hecke correspondence, and the other one is partial Frobenius. So Hecke correspondence works more or less similarly to Shimura varieties. I'll just say it briefly. Now, so the setup, let's say we are, again, we don't start with a level structure, but we want to do Hecke correspondence according to a double coset so some place, and kx is g of ox. Okay, so the Hecke correspondences, as in the classical case, are parameterized by double cosets of in g of fx under g o x. Okay, so so for any, although we didn't start with a level structure, to talk about Hecke correspondence, we need to introduce a little bit of level structure. I'll just write some symbols, and I think it's pretty much self-explanatory. So as Hecke correspondence, we need to put a level structure at X given by this compact open subgroup. And then it will have two maps to the case without level structure. So, and then you can decorate the superscripts by anything you want. You can put iterated or non-iterated and arbitrary lambda. But I need to explain just what this means. So let's say I have some I and I have some level group. Okay, so let's, for simplicity, assume this is inside kx, some finite index. Well, assume it's well, we can call it a level group. So level group has to come from some algebraic subgroup. So it's maybe where this fancy K is a subgroup of G double bracket T. So this is the infinite dimensional group, the positive loop group, and is some finite codimensional subgroup. That's the algebraic analog of compact open in a Piadio group. To construct the moduli problem, we need some algebraicity of this level group. But in practice, this is not an issue. In practice, we take it to be a congruent subgroup, or Iwahori, parahoric. So all these come from k points of some infinite dimensional algebraic group, pro-algebraic group. Okay, and then to define this moduli problem, the only thing we need to well, there's subtlety, but the strategy is just to ignore that subtlety by requiring the legs to be away from X. Okay, so we require all the legs are away from X, and then all the bundles are equipped with Kx prime level structures. And then the same diagram, but all the maps should respect the kx level structure, kx prime level structures. Okay, so typically kx prime could be an Iwahori subgroup. This means this means you have to classify some auxiliary data. So EI, a vector bundle, so in GLN case, with such a level structure, it means a bundle with a full flag of the fiber of EI at X. And then all the maps have to preserve that full flag at X. And that only makes sense if your lag is away from X. Okay. So this stack, by our convention here, it lives away from X. Okay, so there's some. And these two maps are just basically forgetting a level structure. One of them is just a natural forgetful functor, forgetting the full flag in this example. The other map is something like first multiply by G and then forget. So, okay, so this is a little. I did not. Maybe I don't write down details here. We can postpone the detail later. But what we need to know is that the nature of this correspondence. Let's just give it a shorter name, just some correspondence, kx, g, kx. So both maps to Shtuka are finite étale. Okay, so the fibers, just as in the classical story, fibers are look like the difference of the level groups. This at least is saying there are this many points in the fiber geometrically. But again, the fibers there are more structure to the fibers. It's in the case of congruent subgroup, principal congruent subgroup. Let me not talk about principal congruent subgroup. But the key point is map is finite étale. So we can, when we pull back sheaves, it behaves well. Sorry, so not finite étale everywhere, but I have to restrict. Restrict to here, it's finite étale. Okay, so these Hecke correspondences, they actually give, you can compose two of them. So you can compose two of them, and they can be organized into an algebra map from the Hecke spherical Hecke algebra. So let's see. to the algebra of correspondences, self-correspondences of Shtuka, or maybe you can always decorate it by some bounds away from, well, let's say finite étale. So this is it's a category of self-correspondences of this guy, where both maps are finite étale. And it makes sense to compose two correspondences like that. You still get a finite étale correspondence. And the statement here is that this composition as correspondences is compatible. Well, maybe I need to pass to the Grothendieck group. Yeah, it's some kind of linearized version. It's not really something like that. I need to talk about the operation of sum of two correspondences with coefficients in Z, something like that. But the basic point here is that convolution of two Hecke functions correspond to composition of correspondences. So this Hecke algebra acts on Stuka moduli space by correspondences. So that's not new to us. It appears in automorphic in modular curves. What's really new in the Shtuka case is there's another construction called partial Frobenius. And it's emphasis on partial, and this is refers to we can have several legs, several places of modification, and roughly Frobenius is only applied to one leg. Okay, so on the level of algebraic varieties, this is easy to define. Suppose I have consider the iterated version. So partial Frobenius is a map. So for indices, you need to cyclically permute the indices. And remember here, the lambda goes with these indices. So lambda 1s now will appear in the last step. So partial Frobenius for 1 will give a diagram like this. In the bottom, this is sends the effect on the legs is okay. So x2, xr, and the frob of x1. Okay. So the definition of for 1. So for 1 sends. Of course, I have already told you how it acts on the legs. So I need to tell you how this chain of G-torsors become another chain of G-torsors. And it's very simple. It just shifted by one step. So now the new E0 is the old E1. ER is identified with tau E0, this whole thing is just one step. And then we go to tau of E1. We finally tie back to tau of E1 using tau of alpha 1. Okay. So it's just shift to the right by 1 unit. And you can check the lag, how lags change, right? The first lag now becomes the last one up to Frobenius. The other lags stay the same, but then the index is shifted. And this is the morphism of moduli spaces. Now, if I iterate this operation, r times, what do I get? So I will then have to shift E0 all the way to this ER place, and then starting there. Then this chain of bundles is just the Frobenius pullback of everything here. Okay, if I shift by R, so this is exactly the total Frobenius, a Frobenius applied to everything. Yeah, so in this sense, partial Frobenius gives a decomposition of the total Frobenius into R steps. So that's why it's called partial Frobenius. And like total Frobenius, this is a homeomorphism. So this is as far as a tau cohomology is concerned, you can treat it as the pullback by this map gives an isomorphism on a tau cohomology. It's purely inseparable. The points here are just the reduced fibers are just one point. Okay, so I have talked about all the constructions on the level of spaces. Now I want to add some sheaves to the space. So we are interested in the cohomology of moduli of Shtukas. So just why are we interested? Well, it behaves like Shimura varieties. This recall from Sophie's talk. So it actually reminded me, Sophie, did you use K for the level structure? Yes. Okay, thanks. So, well, this M can be either Shtuka or Shimura varieties. Let me just some modular variety. And if we take co-limit when we pass to finer and finer level structures, this cohomology space will carry commuting actions of, on the one hand is the G adels, well, in the finite adels, maybe in the number field case. On the other hand, it's Galois action. Okay, so this cohomology means the geometric generic fiber. So in the Shimura variety case, or in the case of moduli of Shtukas with one leg, this is completely parallel. Now, if we have multiple legs, so this here, there's a mu, and we explained yesterday, mu is the same as lambda. So now in the Shtuka case, we have the freedom of adding legs. We can have a tuple of mu's or lambdas. And if we shrink the level, again, we're going to get G Adel acting. This is the by Hecke operators, by Hecke correspondences. So this is the limit version of the Hecke operators by constructed there, their effect on cohomology. This now lives over, I'm again taking a generic fiber. So this will be the generic fiber over the generic point of x to the r. So it will carry Galois action not of the f, but of the function field of x to the r. Okay, so this with function field, some much more complicated function field of dimension transcendence degree r over fq. So what's going to happen is that Drinfeld and more generally Laforgue show that this action actually factors through a product of, well, maybe the Weil group. The Weil group version factors through the product, the rth Cartesian product of the Weil group of this function field, which is, well, there's a canonical extension to this. So this group a priori is much more complicated. This is just the Cartesian product of our Weil group for the global field.
Sorry, can you repeat again what's the top group?
Top group is, the question is what's the top group? The top group is the Weil group for the Weil version of the absolute Galois group of this field, which has transcendence degree r over the base field. It's not something that we want to, not directly related to Langland's program, because its transcendence degree is bigger than 1. But it maps to, by functoriality of pi 1, each projection induces a map on fundamental group and on the Galois, absolute Galois groups of function fields. So we do have r different projections to the Weil group of single f. And amazingly, this action factors through this rth power of the Weil group of f. And this kind of structure is precisely given by the partial Frobenius. So with the help of partial Frobenius, one is able to show that it factors through this. Well, not really factors, it's not surjective either, but this partial Frobenius structure provides the extra structure you need to make this Cartesian product act. Yeah, so the two geometric constructions are responsible for the two pieces of symmetry that's acting on the cohomology of moduli of Shtukas. So let's be more precise about what we mean by cohomology and give indication of how these actions are constructed. So one complication we mentioned is that Shtuka bounded aversion is not always smooth. In general. So the natural cohomology to consider is intersection cohomology. So I'll just I'll use IC lambda to denote intersection cohomology sheaf on many different spaces, unfortunately. But they are all related, they are all smooth locally the same. Okay, so this can mean the intersection complex on either GER lambda less than or equal to lambda, or the Hecke version, or Shtuka. Well, Hecke I. Okay, so in these cases there's a tuple, so I can also put tuple. The construction in the study of these intersection complexes is really one of the key new ingredient in Vincent Laforgue's work, as he uses deep results about the properties of these IC sheaves, especially when you have not just one lambda, but a tuple of lambdas. But I don't have time to elaborate on that. So let's just give one example. Well, just give definition in one case, which is the iterated case. Okay, so definition I already gave. So this IC lambda means, in the Shtuka case, the IC sheaf of this algebraic stack, which is defined. But concretely, what is it? We have iterated version. This iterated version maps to the Hecke version by forgetting the last step where you tie back to E0, tau E0. And the way we define this bounded version is by map it to the quotient Grassmannian. Technically, I also need to divide by something like an automorphism group of the formal disk, but it doesn't affect intersection cohomology complex. So this map records the relative position of EI minus 1 and EI. So this ith step in the modification near the lag will give you a pair of lattices in the case of GLN. The relative position of those two lattices will give you a point here. And this is less than or equal to lambda. Oh, yeah, so product with the iterated version, we have R factors bounded by lambda I. And this IC lambda starts life here. So it's the intersection complex that measures the singularities of each of these Q GER less than or equal to lambda I. Or, I mean, it's the same as thinking of them as intersection complex on GER, because that is they are related by a smooth map. So this is a more primitive, and then it turns out this map is also formally smooth. So the IC here for Shtuka is the pullback of this external product of IC sheaves. Okay. So again, roughly speaking, the singularities of this iterated Shtuka is the same as the singularities of GER lambda I, the product of them. And in the iterated case, we can really relate them by a formally smooth map, and IC pulls back to IC. So if you, so you may wonder, probably in practice, we maybe only need to work with a minuscule lambda. Why should we worry about singularities here? But in fact, in Vincent Laforgue's work, it's crucial to use all lambda and also the freedom of having multiple legs. So we have this sheaf, and then we can define I'll give a definition. So I want to define something called H I. Well, sometimes H I W, which well, Congxue will talk more about it. This I is a finite set. This W is a finite dimensional representation of the dual group power to the power I. Okay. So I'm going to. It's going to be a long definition. I'm going to do it in steps. So this will be the cohomology of moduli of Shtukas. Okay. But why such parameters? Well, I, we have already seen, it indexes the legs. This W, well, before knowing what W has to do with all this business, we can first say that since W decomposes into irreducible representations, so this is QL bar algebraic representation. So it decomposes into irreducibles, and each irreducible looks like external tensor of irreducible representation of each factor with highest weight lambda I. So each W can be decomposed into these irreducibles, and our definition of HIW will be additive. Okay. So we only need to define the case where W is the external tensor of a bunch of irreducible representations of G to the I, G check to the I. And at least now we see the data lambda here. The same lambda also show up in the definition of bounded Shtukas. Okay, so we've matched the parameters. Now we have this choose an ordering. This gives Shtuka iterated version less than equal to lambda to x to the r. So this, let's call this pi. On the one hand, this moduli space carries the intersection complex. We use the usual normalization of intersection complex so that it's a perverse sheaf. Maybe it's better to normalize it so it's relatively perverse, but okay, let's not worry about that. We have a curly H. We first define curly HI and this external VI to be the whole complex push direct image complex of IC lambda. Okay, so this lives in the this lives in the not quite in the sheaf derived category of constructible sheaves of x to the r, but in the completion of it. So this because this moduli stack is not of finite type, so we can only approximate by bigger and bigger finite type open subsets. Each such truncation will give a constructible sheaf, a complex on x to the r, and can we can take its colimit. Then take that as a definition of the direct image. And this straight H again, this is the generic fiber, geometric generic fiber. Of this curly H. Okay, the curly H is basically the sheaf, and I restrict to the geometric generic point. That gives a vector space. This is still can be spread over several degrees. So it's a complex of vector spaces. Can you repeat the question? What coefficients? It's the QL bar coefficients. Yeah. So there's an obvious issue with this definition. That is, we've chosen an ordering of I. Okay. But our notation did not reflect that. So in fact, this curly H, curly IW, or straight H version is independent of the ordering on I in a canonical way. Yeah, this is the reason it can be traced back to some important properties of Affan-Grassmannian or Bailin's and Drinfeld Affan-Grassmannian. But just in one sentence, you can give a definition that does not use an ordering on I. Can define it by.
There is a question in Discord asking whether the bounded Shtuka moduli space of Shtuka is a finite type.
Bounded is what?
The bounded moduli space of Shtuka is a finite type.
Oh, the question is whether the bounded version of moduli of Shtuka is of finite type. So the answer is it's locally of finite type, but not globally. And that roughly it's an increasing union of finite type open substacks that causes the push forward to be not constructible. Okay, so we can just define it using this non-iterated version. It also carries an IC sheaf, which is a priori, it's not clear how to calculate it, what it looks like. In the iterated version, we related the Shtukas to product of Affan-Grassmannians, and we can make calculations there. This is more complicated, but still it can be understood using Bailin's and Drinfeld Grassmannian, which I did not define, but that's some keywords here. So it's some kind of a non-iterated version of Affan-Grassmannian. Yeah, but this reflects, if you define it in this way, then you also need to show, or it would be nice to show this definition agrees with the iterated definition. Okay, and that's a key property of these IC sheaves on Bailin's and Drinfeld Grassmannian that plays a role in geometric satake. Yeah, maybe I should say a few words about geometric satake. I hope maybe a little bit more discussion will appear in Xinwen's lecture tomorrow. So what we are doing here is that we are pulling back sheaves on this Q GR. So geometric satake is can be formulated using perverse sheaves on this Q quotient version of Grassmannian that are constructible in the sense that they are supported only on finitely many strata or lambdas. And so it's yeah, we only need the QL bar version for this talk. And finite dimensional algebraic representations of the Langlands dual group. There's a so the way we present it is there's a functor in this direction as well. This would turn out to be an equivalence of tensor categories that sends irreducible representation with highest weight lambda to the IC sheaf in the closure of Q GR lambda. So I didn't talk about how to make this into a tensor category and why this functor is a tensor functor. So all those deserve another 3 lectures, maybe. Yeah, but this is a kind of in the background. So it's there's more structure to this assignment V lambda to IC lambda, especially when you start tensoring 2 representations, it will get sent to intersection cohomology complex of bigger strata, and there's a lot of interesting geometry going on there. Okay, so now I have defined in a more precise way what cohomology we are talking about. So then I'll state 3 structures on these cohomology sheaves. So Hecke action. Yeah, this is more or less clear by now. If I have a Hecke operator indexed by some double coset, I have finite tau maps to Shtuka. Well, either iterated or non-iterated. At least restrict away from the point. So these are both finite tau. And the 2 IC sheaves actually pull back. When you pull back to the correspondence, they are canonically isomorphic to the IC sheaf of this middle guy because the maps are tau. In this case, such a diagram induces a map from the direct image complexes of these stacks. So it induces an endomorphism of this complex both restricted to x, remove little x. Okay. So here W is the same data as these lambdas. Okay, so we get a, and it's compatible with the algebra structure on the Hecke algebra. So gives a, this is the spherical Hecke algebra. The action on the curly H I W for any W restricted to away from X. This algebra is acting. And if you restrict to the generic fiber, then there is the whole global spherical Hecke algebra. Can act, okay? So that's one structure. Hecke action, this is a shadow of the G-Adel action when you go to infinite level structure. Here we stick to no level structure. We can only see the Hecke action. Yes, so. And second is partial Frobenius. Action on H. And this here you will see why it is useful to introduce iterated and non-iterated versions of Shtukas. So recall partial Frobenius is a map okay, so you have a cyclic permutation of the indices. This certainly induces a pullback map. So I take the IC complex here. Since this is a homeomorphism, it pulls back to the IC complex here. And then I push forward. I get, what I get is the following. So I'll just write the answer. So first, let me do the whole diagram actually. So I prefer to think, although I introduced an ordering, well, introduced ordering, but for the legs, I don't want to use the ordering. Okay, so in both cases, these legs are indexed by I. Forget the ordering. And then this partial Frobenius is compatible with the Frobenius on the first coordinate and identity on the other coordinates. Well, not the first, but the, okay, it is the first. I'm still sort of using the ordering, but here I have renumbered the legs such that one still goes to, the first coordinate still goes to first coordinate. So the IC pulls back to IC. If you just chase the diagram, you will get a map HIW. So this is for X1. Mapping to the same HIW. So this is the cohomological consequence of the partial Frobenius. You have the same sheaf, curly HIW, pull back along the Frobenius map of the first leg. So this is not the sophisticated Frobenius. It's just Frobenius on the curve. And that, in fact, is isomorphic. It is a canonical isomorphism with the original complex. But the construction uses the iterated version. Okay, so both sides, you don't have to. So it's canonically independent of the ordering of I. But in order to construct this isomorphism, you choose an ordering, cyclically permute the legs, and you have a map there, and then you somehow forget use that to construct a map, and then you show that this map is actually independent of the ordering. So this is really a place where you really need to introduce the iterated version. And in fact, more generally, you can do. You can call any element I in I, call it 1. And this gives you, so Frobenius on the ith factor. There is a canonical isomorphism with with itself. So, and all these for different i's, these phi i's commute with each other, and their composition is the total Frobenius, is the natural Weil structure on H. Okay, so that's the partial Frobenius structure.
So you implicitly are also claiming here that this phi I doesn't depend on the ordering of the other indices, but only depends on the I, because a priori it also depends on somehow how you really order.
Yeah, right. So the question is, this notation suggests this phi I does not depend on how you order I. Well, you order I, maybe to construct it, you put I first, but then you still have the choice of ordering the other elements. And this does not depend on that choice. That's right. That's something to show. But how much time do I have?
3 or 4 minutes.
Okay. So I just want to mention the last piece of structure. Last piece of structure is called factorization structure. Or maybe fusion. So I want to describe how what happens when legs collide. So basic example is when you have, well, before we put any bound, say we have 2 leg case, and then restrict to the diagonal. So this is 1, 2. It's a non-iterated version. Okay. So this just means I'm doing a one-step modification at 2 points. What if those 2 points coincide? Well, I'm just doing a one-step modification at 1 point, and that is the one-leg Shtuka. Okay, so that's a Cartesian diagram before you put any bound. Now if we consider bounds, then what happens is the bounds add when you go to the diagonal. So if you have lambda 1, lambda 2 here, the bound here will be less than or equal to lambda 1 plus lambda 2. Okay, so you have here maybe each step you're not changing your bundle too much, but now on the diagonal you're making 2 steps. Implicitly you're making 2 steps of changes, and the bundle can be further away from original bundle. So bounds add. Now there's more precise statements about singularity, how the singularities of this relates to the singularity of that, and it can be summarized as follows. In terms of these curly HIW, so I need to restrict to a diagonal. So let's first restrict to the small diagonal. Okay, here I consider multiple legs. Here I consider only one leg. So on the level of representations, the index set here is a representation of I copies of G hat. So in the one leg version, I only have one representation of G hat. Here I take the restriction to the diagonal. Okay, so for the G hat also diagonally embeds into G hat I. And the claim is that there is a canonical isomorphism between, so this is called a delta, the restriction of this HIW to the total diagonal, small diagonal, to something defined for the one leg Shtuka, except that this index, which is basically a sum of IC sheaves for different bounds, becomes more complicated. If you start with just the tensor product lambda v lambda i's, here you will still have the same vector space, but viewed as a representation of the diagonal G hat, it will decompose in general, right? So it's not irreducible. It has a tensor product decomposition. So that means this sheaf is a direct sum of various H point V lambdas. Okay, so it becomes more complicated. But the formula is extremely elegant. You restrict to the diagonal for your legs, and at the same time you restrict your representation also to the diagonal G hat. So this more generally, if you restrict to a partial diagonal, so this can be, you start with a surjection of finite sets, that'll give you a partial diagonal. And at the same time, it gives you a partial diagonal of G hat. And you have a similar isomorphism. Okay, so you start with HIW, restrict to the partial diagonal of the curve. That's canonically isomorphic to HJ for the representation W restricted to the partial diagonal of G hat. Okay, so basically these are the necessary structures to proceed further, leading to Vincent Laforgue's construction of Galois representation out of cuspidal automorphic representation.